Okay, I want to talk a little bit in this segment about optical instruments. And this isn't really meant to replace your text and what it has to say about optical instruments and how they work, but more as a little supplement to call a few different things out that may or may not mention there. As we discussed before, in the eye is just a simple lens retina system where what we mess with or adjust is the focal length of the eye. And for various reasons, that adjustment gets to the point where it doesn't have the range it needs. And so you need glasses to either deal with far vision or near vision, or as you age, both perhaps. Um, when we talk about cameras, however, what we do is not adjust, well, okay, so you can take one lens off and put another one on, and that's adjusting the focal length. But when we talk about cameras, what we really do when you turn a when you turn the camera lens to focus it, what you're actually doing is moving the lens in and out, right? So it's not the focal length we're messing with at that point for a camera to get things where we want. It's the distance to the image. All right. So we're still playing with this equation. It's just the focal length is now fixed and we're varying the distance to the image. Whereas with the human eye, the focal length varies and the distance to the image is always the same. When you talk about cameras in particular, we'll talk about something called f-stop or f-number. And that's just the focal length divided by the diameter of the aperture. All right. Why is this important? Well, diameter of the aperture determines how much light you're letting in, right? On wide diameter, you're letting a lot of light in. Small diameter, you're letting just a little bit of light in. Large diameter, you can actually take a faster photo because you're getting a lot of light in. Small diameter, you may need longer exposure to get the image you want. And these are issues we worry about when using cameras. When you start talking about telescopes, which is not really what we're doing here, telescopes are a little different in that it's a lens system, right? We got an object lens, we have another recting lens, and we have an eyepiece. The recting lens is so that we actually see the image right side up. Because if you use just a single image in single lens, it's going to be upside down. Um, and we talk about magnification for telescopes a little differently as a ratio of angles. Not really all that important here. More important if you start dealing with much longer distances, right? Where you're talking about something that's operating probably a bit more like a telescope than just a regular camera. All right, what can go wrong with lenses? There are a couple of different things that can go wrong with lenses, and one of them you're actually familiar with, chromatic aberrations. And you're going to say, I'm not familiar with chromatic aberrations, but you are, because you've probably at some point in your life seen a rainbow. The same effect that gives rise to a rainbow is what gives rise to a chromatic aberration in a lens. Chromatic aberration in a lens simply means that the focal length for blue light is different from the focal length from red light, and there's a continuum in the middle. What does that mean? That means you don't have a single place where you can put your CCD camera or your film and have everything focused, right? Because the focal length is in fact a function of frequency or a function of wavelength. You can never bring everything into focus. So chromatic aberration, worrisome thing, means you have to have a different lens, right? Because the material you're using is the problem. And the chromatic aberration we see that gives rise to rainbows is the fact that this effect happens in water, that the water droplets in the air bend red light and blue light differently, and they spread out the spectrum, the visible spectrum, as the light bounces around inside the raindrop and then comes out towards you. And whenever you see a rainbow, the sun will be behind you. Um, Spherical aberrations. This is something, if you are old enough, you will remember that the Hubble Space Telescope, when it launched, we discovered that it had some spherical aberrations. Spherical aberrations means quite simply that the focal length out here for light hitting here is different than the focal length for light hitting closer to the middle, right? And so again, that means there's not a single place where you can put a um, a lens, right? There's not a single place where you can put a lens. I'm not lens, pardon me, a piece of film, right? There's not a single place where you can put a piece of film to image this. Now, the way we fixed the Space Hubble telescope is we had to go in, we had to put in another lens, right? Before we got to the imaging CCD, had to put in another lens. That lens corrects the physical aberration, the spherical aberration, pardon me. That lens corrects the spherical aberration and focuses the light on the CCD in the Hubble Space Telescope appropriately and gives us all these great photos that we get from space. All right, that's it on this piece. I'll talk to you next time.